this too. Just kidding, we won't. All right. So last class we looked at this problem, right? We did it at the very end. We said calculate the deltaG at 25 degrees and determine whether the reaction is spontaneous. So they give us the deltaH and they give us the deltaS. We have the formula deltaG equals deltaH minus T deltaS, right? So basically all we're doing is plugging and chugging for part A. And then how do we determine if it's spontaneous or not? DC there. No, I'm saying before that. So once we solve for deltaG, how do we tell if it's spontaneous or not? What indicates? So the take-home messages with deltaG that we've been talking about is if deltaG, hold on. If deltaG is negative, that indicates spontaneous reaction. If deltaG is positive, that indicates non-spontaneous reaction, right? So what we're doing is we want to see, is this reaction spontaneous at 25 degrees in part A? So what we do is we take the deltaH, it's 95.7 kilojoules, but then notice that if we subtract the temperature, which we could put either thing, but if deltaS is in joules per Kelvin, what must the temperature be in for the units to cancel, Ida? Kelvin. So we convert 25 by adding 273, and that gives us 298 Kelvin temperature, right? We're going to plug that into this equation, but the only thing is this will give us our answer in joules. This is given in kilojoules. So you can either convert joules to kilojoules or kilojoules to joules. I'm going to convert the kilojoules to joules. Okay. Or should we do it in, let's convert the joule. Nah, I don't like working with decimals and things like that. So I'm going to convert this number, 95.7 kilojoules. 1 kilojoule is 1,000 joules. So I get 95,700, oops, too many zeros, joules for the deltaH. So deltaG equals deltaH, which we said was 95,700 joules, minus the temperature, which is 298 Kelvin, times the 142.2 joules per Kelvin. So let's go ahead and plug in 142.2 times 298. Somebody shout out the answer. Confident about that? 42,375 joules. So Kelvin cancels. That puts our answer in joules. 95,700 joules minus 42,375 gives us what? It gives us positive 53,000. How much? I don't know. 5324 joules. So the deltaG for this reaction is a positive 53,324. Since deltaG we found was positive, that means the reaction is non-spontaneous. Okay? Everyone comfortable with that? Now, part B says if the reaction is not spontaneous, is it not spontaneous? Yes. Then calculate the temperature at which the reaction becomes spontaneous. So we could raise the temperature a lot and see if that makes it negative. But if it, we want to find the exact temperature. So what's the best way to do that, Jack? What is the temperature in which the deltaG goes from negative or positive to negative? Where's the flip point? When deltaG equals 0. So for this part, we set deltaG equal to 0. So now we're going to have, we still have the equation deltaG, let's see, deltaG equals deltaH minus T delta S, right? We want to find the temperature. We can plug this in to make it be 0. So when deltaG is 0, that's when this reaction switches from spontaneous to non-spontaneous. Everybody see that? If we're doing a reaction where we're doing like a solid becoming a liquid, when deltaG is 0 is the temperature at which that melting point is the cutoff, where above it, it does melt, below it, it doesn't. Or if we're looking at a freezing point, below that is when it freezes, above that is when it doesn't freeze. So basically, all these things like melting points, freezing points, boiling points, and things like that, people like, you could just boil a liquid and see when it is. But if you want to theoretically calculate that, you can use these values because a lot of these things are readily available. So to do this, we're going to just plug in 95,700 minus T times 142.2 joules per Kelvin. So we bring this over. So that equals 0, right? So what I'm going to do is I'm going to add this other side over just because I don't like dealing with negatives that much. You could bring the negative 90, you could subtract 95,700 from both sides to make a negative 95,700 equals positive 142.2, or equals negative T times 142.2. I'm doing it the other way. So I bring the T times 142.2 over to the other side. So I get 142.2 times T equals 95,700. I divide both sides by 142.2. What is 95,700 divided by 142.2? Is it 673? 673 units, in this case, are Kelvin. 673 Kelvin. So we subtract 273. That tells us 400 degrees Celsius, or 673 Kelvin, will be the temperature we have to raise this to get it to be from non-spontaneous to spontaneous. And let's verify that. What was our answers? 53,000. Hold on. 53.3 times 10 to the third is 53,000. 673 Kelvin. So we'd have to get above 400 degrees Celsius to get that. Everybody see how we do these problems? Pretty straightforward, right? Not that straightforward, but now you know how to do that for your homework, which is due when? Chapter 17? No, I think that's a different one. That's chapter 18. When's chapter 17 due? That could also be due the same day. Real quickly, Meredith, do you have a free piece of paper? Take it out, write your name on it, pass it on. Everybody who's here will get 2 points extra credit on their final exam in person. If you don't want that because you want to make yourself try harder, just don't write your name on the paper. Okay, Jessica? Because it'll make you be like, no, I'm going to slack off 2 points more. I won't do that. Let's do a quick conceptual question. Oh, now people want to chat. Come to class. Which statement is true regarding the sublimation of dry ice? So dry ice, Bryce. What does subliming mean? You know what dry ice is, though? What does dry ice do? What's its special feature? You ever mess with it? Who helped with the Chem Club? Nobody? What's dry ice, Kayla? I mean, what does it do? So dry ice is a solid and it skips the liquid phase and just sublimes into a gas, right? You can play with it at like Halloween to make witch's brew because it's very smoky and things like that. For Chem Club kind of things, we use it for we'll put it in water. It'll make bubbles we'll make soap bubbles and the little kids can play with it and things like that. It's kind of fun. So regarding the conversion of solid to gas, has anybody ever touched dry ice? Why do you think it has the word ice in it, Ian? Is it hot or cold? Very, very cold. So would you say that the sublimation of dry ice is exothermic or endothermic? Thank you very much, Ian. Endothermic, but that is correct. Okay. Would we say that going from a solid to a gas is entropically positive or entropically negative, Abby? Everyone agree that it's positive. Delta S for this is positive. So gas is more random than solid? Yes? No? What do you think? You two didn't want to sign that? Or you did already? Okay. I thought you were just giving that. Oh, we don't want that. So delta S is positive. So what can we eliminate of these four options? If you ever had a multiple choice test, this is a good way to kind of go about it. So Bailey, which one can we eliminate? Which ones do not have delta S is positive? What letters? B and D. So you see how we do that? And now we can eliminate the whole thing and not have to even worry about that. Endothermic, does that mean delta H is positive or negative, Alyssa? Everyone agreed? Delta H is positive for an endothermic reaction, yes. So delta H is positive, delta H is negative. We eliminate that one. Let's hope the answer is A. Since sublimation is endothermic, cold to the touch, and since a solid becoming a gas is more disorder, we know that sublimation is endothermic. We can say it's A. Everybody see how to figure out a problem similar to this. All right? We comfortable with that? So that's kind of a little intro into Gibbs Free Energy. Let's now look at all the let's look at all the different ways we can solve for all these different things. This is going to help us with our homework. So, we're going to like take a step back. We're going to go back to looking at entropy. Okay? So, do you remember delta H not of a reaction? Anybody remember what this little degree sign indicated? It's not quite the initial. What it is something called the standard state of any chemical. And there was some like definitions that we made, and that was that the standard state for any reaction would be like that substance in its most stable form, whether it's a solid, liquid, or gas. So if it's talking about oxygen, it would be oxygen in the gas form, right? Because oxygen's in the gas form. We don't have liquid oxygen and stuff like that. If it's a solution, we say it's 1 molar. If it's something else, but it's basically like the most, we're going to take this standard state of things and we're going to make that equal to 0 is what we did in delta H. Remember when you had to like do the equation summation of all the reactants and all the products? Whenever you had like a compound like HCl, it would never have an enthalpy of 0. But if we talked about hydrogen gas, that had a value of 0. Oxygen gas had a value of 0. Iron solid, because that's the way we find iron metal, had a enthalpy of 0. So we're going to learn about the standard state for entropy, and it's going to be a little bit different. Okay? So the standard state of a material is is at a defined set of conditions. If it's a gas, we say it's a pure gas at exactly 1 atmosphere. If it's a solid or liquid, we say it's the pure solid or liquid in its most stable form. So when we're talking about carbon, are we talking about graphite or diamond? What's the most stable form? Anyone remember? Angie? What's more stable, pencil lead or diamonds? Remember I told you, like, do not ask for diamonds because they're going to eventually spontaneously convert into graphite. But then Ella had to go look it up on the internet, and she thought the internet is more realistic than what I'm telling you, which it probably is. But actually, graphite is the more stable form, okay? But what was it, Ella? Million years? Billion years? 2 billion years, okay? So if you're gonna plan on having your diamonds for more than 2 billion years, it could turn into graphite, and don't be too upset when it does. Don't say that I didn't warn you. But basically, this is just saying all this stuff. If it's a solution, it's at 1 molar. You don't really have to worry about any of that stuff. The third law of thermodynamics, you're probably wondering. We learned about the second law, right? We learned about the first law. What is the third law? The third law is the absolute entropy of a substance is the amount of energy it has due to dispersion of energy through its particles. I don't think that was the third law. That's not the third law. The third law is that a perfect crystal at absolute zero has an entropy of 0. So basically, at absolute 0, what does that mean, Jessica? 0 Kelvin, negative 273.15 degrees Celsius. Has that temperature ever been achieved on Earth? No, it has not. Okay. So it's like this hypothetical, theoretical thing. But if we state that the perfect crystal of any substance at 0 Kelvin is the perfect form of it, we state that entropy equal to 0, then any variation of that would be positive or negative. What do we think, Ida? So if the perfect crystal is this thing at 0 degrees Kelvin, anything other than that, would it be more positive or more negative? It's going to be not perfect, right? And when you vary away from perfectness, we vary into disorder. So the more disordered we get, the more positive. So basically so with entropy, delta H was, when with delta H of the pure stuff was 0, we could have negatives and positives in relation to that, right? Some things absorb heat, some things gain heat. With entropy, the perfect crystal is 0. Anything other than the perfect crystal is no longer perfect. Therefore, it's always going to be positive. So there's actually going to be no such thing as negative entropy in the cases of the standard state of chemicals. Okay, so some chemicals did have negative delta H with the knot. And basically that's saying that the delta S knot of all these different things we're going to look at, people have figured out some way to like do it. I don't know how they can like figure out how much entropy a piece of diamond at 25 degrees Celsius is compared to that graphite at 0 degrees Kelvin, but they made some way, and they've basically made a bunch of tables where we can use these values to our thing. So therefore, every substance that is not a perfect crystal at absolute 0 has some energy from entropy, right? So all of these will be positive. The entropy of everything is going to be positive compared to that perfect crystal of it at 0 Kelvin. So when we say S naught, it is an extensive property. It does depend on the amount of a substance. If one person has, let's just say arbitrarily 5 kilojoules of entropy, if we had 10 of them, do we all agree that we would now have 50 kilojoules of entropy? Because one person has 5, but now if we have 10 of them, they each bring 5, we'd have 50 kilojoules of entropy, right? So that's what an extensive property means, is the amount matters. The more of it you have, the more entropy you have. The less of it you have, the less entropy you have. So entropies for 1 mole of a substance at 298 Kelvin for a particular state you may have heard the term allotrope before. That just means like the state it's in. So I think diamond and graphite are allotropes. A particular allotrope, a particular molecular complexity, a particular molar mass, and a particular degree of dissolution are seen in the following table. So basically, if we had a traditional textbook, I mean, and there is a textbook for this class, I just don't assign it because I don't believe in that. But in the back, you know how in the back of the textbooks, there's all those tables that you're just like, what the heck are all these tables? One of those tables would be the standard molar entropy values. And actually, it is not delta S naught, it is just S naught randomly, because with delta H naught, we were looking at the difference from that pure thing. Since all of these things we're stating in the perfect form are zero, everything is going to have a positive, non-negative value, so we don't have to look at the change. So let's take a look at some of these different things, okay? What are some, so each of these things, let's try and look at, let's look at fluorine versus chlorine. Everybody in their mind have an idea of where fluorine is on the periodic table in relation to chlorine. I mean, you might not have to know exactly the spot, upper right. We should know where fluorine is, right? That's the upper right besides helium. And chlorine is a halogen below it. So what do you notice about fluorine versus chlorine versus bromine versus, I don't even know, iodine's not on here for some reason. Well, actually, let's not compare that one because that doesn't make our trend good. Fluorine gas versus chlorine gas. Which one has a larger molar entropy? Carissa, fluorine or chlorine? Huh? Chlorine. So why do we think that is? They're both gases. Do you have any thought on why fluorine would have a lower entropy than chlorine, or why chlorine would have a larger entropy than fluorine? What's a property about? They're both in the halogens. What do you think, Robert? It's got more protons and electrons. So those protons and electrons can be a little bit more disordered. The more net size you have, the more net microstates you could have. Thus, the more entropy you could therefore have, right? So we'll look at each of these things individually. Some things to realize. Water liquid is 70, water gas is 188. We've already kind of looked at that, right, Justin? Why would liquid have a lower entropy than gas? Which one is liquid or gas? Very good, right? There's like, if you had a sample of liquid water versus after it evaporates, the liquid water is stuck to the bottom of, like, let's just say a cup. So it's open to the air, right? But if we let that liquid water evaporate, it's now spread out and it's going to move around. Wasn't there much more different possibilities for that gas because it's spreading out and moving anywhere than that liquid, which is kind of confined to the bottom of that container, right? Ella, did you have something to add, or is that what you're going to say? Okay, perfect. So we've already talked about why liquids are less entropic than gases, solids even less than liquids, which would thus be less than gases, right? Let's look at 5 different noble gases. We have the entropy: helium as 126, neon 146, argon 154, krypton 163, xenon 169. What we notice is entropy increases as the molar mass increases, and this goes back to what we were just talking about, right? The bigger the molecule, the more complex it is, the more protons, the more electrons, the more orbitals it's occupying, thus the more possibility for variation. So in general, the larger the molar mass, the larger the entropy. It's because the available energy states are more closely spaced, allowing more dispersal of energy of those states. But let's make a big note, that's only for the same physical state will this hold true. Remember when I was trying to compare the fluorine versus the chlorine, and then I was gonna add the bromine, and I was gonna try and like show this, and then I'm like, wait a minute, let's leave out bromine. So why is bromine less than fluorine and chlorine when we just said the bigger molecules are more, have a higher entropy? What do you think, Sophia? Because it's a liquid, right? And liquids are more ordered than that. Okay? Very good. So we cannot compare things that have different so I would not expect you to be able to like give me a trend on something. Like if I ask you on a trend, it's always going to either be all the same physical state or maybe something, maybe the same compound through different phases, but I'm not going to have you compare like water gas versus chlorine or bromine liquid, right? Because that's like, you're like, wait, one has a higher molar mass, which should be more, but the other one is a liquid versus a gas. So I'm always going to make you compare apples to apples, and I'm not going to have you compare apples to bananas. Okay. What did you think I was going to say? Oranges? That's why I switched it just for you, Donatella, to keep you awake. Okay. Um, the less constrained the structure of an allotrope is, the larger its entropy. So, actually, this is weird. The fact that the layers in graphite are not bonded together make it less constrained. So graphite actually has higher. So I don't know what the carbon is at 0 Kelvin that would have 0. So you remember we said there's the perfect crystal at 0 Kelvin, and I thought that graphite was lower. Well, in this case, diamond has a lower entropy than graphite. And what is graphite used for? What are some things graphite are used for? Pencil lead, very good, right? And the reason is when you write on it, a layer of it remains on the paper. Does that happen with diamonds? Does a little layer of diamonds? If that was the case, it'd be like, oh, let me touch your diamond and rub off a little bit of diamond powder, and you could like combine it all to make, I don't know. You could do that with gold powder, but I don't know if diamond powder. But diamonds are extremely strong, right? People use diamonds for like cutting things and things like that, like diamond cutters and stuff like that. Anybody ever heard of that? I've heard of it. I don't know the exact situation, but so I don't think you have to worry about allotropes because there's not many allotropes. And so basically what an allotrope is two of the same things, but different versions of it. Diamond and graphite are one example. I can't think of any other allotropes, but I'm sure there's a lot more. Feel free to look that up on your own if you want to do that. So what else do we see? Larger, more complex molecules generally have larger entropies. So if we look at these two things, even though argon has a larger molar mass, nitrogen monoxide has a higher entropy. Who can tell me why that could be? Why would argon, which is actually has a molar mass of 40, so it's technically a bigger molecule, but the smaller nitrogen oxygen molecule has more entropy? Someone give me a concept on that. Kiana, what do you think? Hmm? I think they're both gases. Any thoughts? Zaira, what do you think? So argon is bigger than nitrogen monoxide as far as molar mass, right? But nitrogen monoxide has a larger entropy. What could be a justification for that? Very good, right? What does the two atoms mean? The two atoms can be here, but they have vibrations, right? So now the big argon can like turn, it can spin, but so can the nitrogen monoxides. They can turn and spin, but they can also vibrate. So vibrations are going to make a difference. So what we're going to see that with nitrogen monoxide versus nitrogen dioxide versus N2O4, you have more bonds, more vibrations. I mean, that's not a perfect comparison because the molecule is getting larger also, but the more bonds you have in a molecule, the greater its entropy will be. So if we look at these two compounds here, carbon monoxide versus C2, H4, they have the exact same molar mass, 28 and 28, but the acetylene has a little bit higher entropy because it has 5 bonds that can have these vibrations, whereas the carbon monoxide only has the 1 bond that has vibrations. So in general, more complex molecules generally have larger entropies because there's more energy states are available, allowing them more dispersal of energy through those states. So as we said, we have this translational motion where they can just move up, down, left, right. We have it where they can rotate, and they also have vibrations within that bond. So all of these things help give more microstates. We had said earlier that a solid versus an aqueous solution is more random, right? Generally, solids that are dissolved have larger entropies than their solid counterparts, okay? Because they're spread out more. And that's just general rules for entropy. So that's like that. I could easily ask that kind of question on the final exam. Okay, the final exam will be multiple choice. I haven't decided yet if I'm gonna do Scantron or not, just because that one I have more time, and sometimes people just suck at filling in a Scantron. Anybody ever notice that? That like you fill out your Scantron wrong? Don't do that. Okay. In the future, yeah, and that sucks. And then also when people erase, it also sometimes marks it wrong. And that's annoying for me when I'm going through. So since I have to go back and look at everything anyway, I might just make it to where it'll still be mostly multiple choice, but that way it gives me the ability to put in a couple short answer questions. Okay. So be ready and I will let you know next week. If you're not sure whether it's going to have a Scantron or not, because you did not pay attention next week, what do you think you should do, Valerie? Get one just in case. Wonderful thought. Okay. But you can always not use it. You can't use it if you don't need it, right? I mean, you can't not have it and use it. So think about that. So this is all comes into play. So if one way we want to find out the delta S of a reaction is to use this super crazy equation, who wants to break down this equation for me? Anyone? Donovan, what does this equation mean? Okay, so it looks crazy, right? With this summation sign, but that summation sign just means the sum of. So that just means add up the entropies of all the products. So I put this parenthesis here. I do it like this. I put all the products, add up entropies of all products. Okay. That little n in the front just means that if you have like 3 of something, you multiply that S value by 3. If it's 1 of it, you multiply it by 1. If there's 7 of it, you multiply it by 7. And then you subtract, and you put this in parentheses also. You add up S's of all reactants, and you do them each separately, and then you subtract it after. This is where people make mistakes when they like punch it into their calculator and they try and do it all at once. I like to write out my thing in steps. That would be the other reason why I would maybe make the final not multiple choice. Okay. Still pretty easy to grade a multiple choice exam that without a Scantron. So I still have to decide what I want to do. Or maybe I just make it a multiple choice and give no partial credit. How about that one? Okay. How many people do we have today? Who has the list? Is the list complete? Did everybody sign the list? Everybody else is going to have signed it after Bailey's done. Count up the people for me, Bailey, okay? So, Kayla, so use your voice, those of you who haven't signed it. And whoever's the last one, count it up and write it at the bottom and bring it to me, okay? So, if we have less than double any of these numbers next week, then we're going to make the exam have no partial credit, okay? That makes sense? So, how many do we have? Probably like 30 people here. If any class dips below 60 next week, I'm not going to offer partial credit because I don't want to like waste my whole summer grading. Okay. Or I want people to start coming to class. I'm just kidding. You know, at the end of the day, I'm going to still offer the extra credit, but I just want to scare people. Okay. But tell your friends, like, you better come to class or else we're not going to have partial credit. And do we like partial credit? Did anybody notice the partial credit that was given? Some of us are like, I don't need it. I get 100 without partial credit. Well, good for you. Okay. Keep doing what you're doing. So how do we do this problem? Let's go ahead and do a problem. So everybody, it's 11:37. I'm going to give you 2 minutes to do this. Ready, set, go. Everybody starting it? What do we have to do? Yeah, you do need a chart. I'm just messing with you. Okay, so you would need a chart, okay? I'm not going to have you memorize every single delta S of everything. So if this was a problem, you would have, so I'll either give you the whole list of all the entropies or I'll give you the ones that you need, okay? So in this case, what this equation means is because the products have 4 NOs, we're going to do 4 times the value of NO, so 4 times 210.8 plus 6 times water, 6 times 188.8, and we're going to put that in its own bracket, minus the reactants, 4 times 192.8 plus, so you add up everything in that bracket thing, right? And then once you get it, you subtract whatever's left, plus 5 times oxygen, so 5 times 205. Do you remember this stuff from last semester? Does this kind of ring a bell? You did this same stuff with enthalpy, the standard enthalpies. The major difference was elements that were pure substances. So like for enthalpy, this would have a value of 0 for delta H naught. For entropy, everything has a non-zero value, okay? Because we're never talking about things at that thing. So you would do all of that. Here's all those values right there. So I color coded it for you, but now I'm going to erase it so we can see this. You would get 1,976 minus 1,792. This gives us a positive 178.8 joules per Kelvin. Would we expect this reaction to be spontaneous or non-spontaneous? What do we think, Janessa? The fact that it's a positive value. And I mean, this is the delta S of the reaction. So really, we can't even really say, right? We would have to combine this with the delta S of the surroundings and see if the delta S of the universe was positive or negative. So let's just say it's not, but let's say this was the delta S of the universe. Would this be spontaneous or non-spontaneous? So remember, delta S of the universe is the opposite of delta G. Positive delta S universe meant that it was spontaneous. Positive delta G means non-spontaneous. Therefore, negative delta G means spontaneous. Okay? But this would just be a way to solve for the delta S of the system. And then I could have like maybe give you the delta S of the surroundings and then you'd have to solve for it. But this is all a bunch of fun. Notice that delta S of the reaction is positive, as you would expect for a reaction in which the number of moles of gas increases. So it went from 4 plus 5 to 4 plus 6, 9 to 10. We would expect a positive entropy when we have an increase in the number of gas particles. That's not always the case, though. If you made, which would be kind of hard to do, but technically could be situations where you do make more gas particles, but if they're like super complex or something like that, that could reduce that number and things like that. But in general, for this class, that will almost always be the case. Okay? So that is that. You'll have to be able to do this on the homework. Is this that difficult? This is just review. It's just doing the same equation with different table values and stuff like that, right? Everybody comfortable with that? Excellent. We are flowing. Let's get to calculating Gibbs free energy now. So, anybody ever see this equation before? Cade, you ever seen an equation like this before? The one we just did, right? What's the big difference? It's now looking at G instead of S. This is Jack's favorite thermodynamic function. So explain it to us, Jack.
The overall thing. Sorry, it's the summation of products.
Yeah. So basically, it's the same thing, okay? So, but the only problem with this is with that little knot, that is only representing at standard conditions of 25 degrees Celsius. Do you think we ever do reactions not at 25 degrees Celsius? Yes, we do. So why do we like spend so much time making all these tables of standard entropies and things like that? Anybody have tell me why we waste so much time learning about at that perfect standard condition? Come on, let's think. Yes, Ella. Say it again. Very good. What were you gonna say? Very good, right? So if you use it as a control, like at 25, this is going to be roughly spontaneous. If we're going to do the reaction at 22, it's probably not going to change that much, right? So it's an approximation of the situations that we're going to probably regularly be doing, right? So it lets you know just kind of could it work or not, right? Like if we're trying to like make something and we like you just do kind of like a rough run, you're like, oh, let me just see how much it'll cost me to make this, you know, thing in the back of my house. And you're like, no, that's not affordable, you know, like it's not even worth. But if you're like, oh, if I manipulate a couple of things, it's maybe going to be like a little bit more than that. If I just change one or two things, maybe I can get it in my price range. But if it's just like, no, that's going to be like 50 grand to do, you're like, yeah, I'm never going to be able to like substitute out a name brand thing for a generic thing and things like that. So if we want to calculate the delta G at a temperature other than 25, we use this reaction that we've already learned about. So let's do a problem. Let's calculate delta G at 25 degrees and determine whether the reaction is spontaneous. Okay. So this is the kind of thing we're going to have to do on the test. Zeus, a little bit earlier than last time. Still got some work to do. One of the possible initial steps in the formation of acid rain. Anybody ever heard of acid rain? They used to talk about it a lot back in the day. Anybody ever walk in the rain and just start getting acidified and start melting as you're walking? You know, some people in this class's hair is a little different colors. They walked in some. I'm just kidding. He's not here to defend himself. But what happens is, so acid rain was talked about a lot, especially before the advent of the catalytic converter in California and like all the smog checks and things like that. So LA used to be like super polluted. Okay, let me rephrase that. LA used to be even more polluted. It's still pretty polluted. Any of you here from the LA area? You offended? No, because it's just kind of the way it is, right? But what they said was sulfur dioxide could react with oxygen to form this compound sulfur trioxide, and that would help cause that, okay? So let's look and see if sulfur dioxide plus oxygen will produce SO3. So we're going to calculate delta G at 25 degrees by doing the products minus the reactants. So actually, so we're trying to get, we're using this equation, delta G equals delta H minus T delta S. We are going to use, so we have to find delta H, right? So we go and we use the heats of formations. This would be a problem from Gen Chem A 115A, okay? So this is what you would have done last semester if you took it last semester with Perry. You add up all the reactants or add up all the products, you subtract all the reactants, and would we say that this is an exothermic or endothermic reaction, honey? Delta H is negative. That would be an exothermic reaction, right? Now we have to find delta S, and we would look up the delta S of all of these things. So these values, oh, okay. So that's what this table is. This table has the delta H's over here. So this is the delta H's. These are the S's. So we would do the same thing using the S's to calculate what the entropy of this is. And this reaction has a negative entropy. What does that tell us, Kayla? Does it make sense that this seems like a negative entropy reaction based on the number of gas particles? You have 1.5 gas particles becoming 1. So it's negative. That makes sense. So to find out the delta G of this reaction, we get what we got from the first part, finding the enthalpy. We got what we got for the second part to plug it into the entropy. That 298 Kelvin comes from this reaction happening at 25 degrees C and converting it into Kelvin. Everybody see that? And now, what is the net result of this, Abby? Would this reaction be spontaneous or not? We got a delta G equal to negative 70.9 kilojoules. Everyone agree with that? We would be spontaneous. What do you think, Sydney? Because it's delta G, and delta G negative is spontaneous. So we would say the reaction is spontaneous at this temperature because delta G for this reaction is negative. Do we see how we do all of these math kind of problems? Okay. Here's another one doing the same thing. You would find delta G. So in this problem, for this reaction, estimate the value of delta G at 125 degrees. Does the reaction become more or less spontaneous at this elevated temperature? What they're saying is, does the value of delta G not reaction become more negative, which would mean it's more spontaneous and want to happen even more on its own? Or if it becomes more positive, that means that reaction is becoming less spontaneous. So you still use the same values over here. You just plug in the temperature that is 100 degrees higher, and we get a value of negative 61.5 kilojoules. Bryce, is the reaction more or less spontaneous? What was the value for the last one? Do you have it written down, anyone? Negative 70 something. So if you're going from negative 70 something to negative 61.5, is it getting more spontaneous or less spontaneous? A little bit less spontaneous, right? Let's see. What the heck? So it is less spontaneous. So it was negative 70.9, right? So since the delta G value at this elevated temperature is less negative, so basically what's that telling us is as we raise the temperature, it actually makes the reaction less spontaneous. So is this good information for someone who's trying to make something like for a production company or something? Usually we say, let's heat it up and that'll like make it happen faster. And maybe it does, but now it's happening, it's getting less spontaneous. Maybe that's not the best thing, okay? So that pretty much wraps up most of chapter 17. I don't think there's much other stuff. Let me just double check. This stuff is just redoing things. The last thing is, anybody remember Hess's law? Anyone remember Hess's law from chapter 6? Gen Chem A. Well, we'll talk about this on Monday, but basically it's just where you have a bunch of reactions and you had to add them all together so that they cancel out some of the intermediates and they equal the overall equation. You have to multiply things by a factor or divide them. You have to switch the sign if you flip them, all of that kind of stuff. So we will go into that, but that's straight review. Anybody know when the homework 17's due? Is it the day before? So I just posted, okay, so that's it for today. If you have to leave, you can leave. Let me show you. So we're going to do chapter 18 next week. Chapter 18 is going to be very minimal on the final. I put up the homework for chapter 18. It's due the day after the final. It's worth 1 point, but if you do it, I will give you up to 5 points, 4 points extra credit if you complete it and submit it. You see how I wrote that word extra credit in there? Every single person in the class is going to do it now. Even though every single homework that they're like, oh, I'll just take a 0. It's normal credit. I'll take a 0 out of 10. 4 points extra credit, that'll turn that 0 into a 4 out of 10. That turns that zeros out of 10s you're getting into an F, okay? Do the regular homework instead of only focusing on the word extra credit, okay? Have a wonderful weekend. Aloha. Happy birthday to those of us who had a birthday in the last 2 days. Yes.
Question about calculations for this lab.